So, welcome to Advanced Aerospace Structures. Today, we'll be covering stress concentrations. And the idea of stress concentration is quite important in aerospace designs because you're going to encounter them quite a bit. Stress concentrations will occur quite significantly. They occur in areas where you have stress gradients, they occur in a small localized area of the structure. And when you have gradients that are quite significant, we will consider these areas as high stress. It could be due to geometric or material discontinuities, like a hole or a material change. We switch from one material to another. Typically, you can also form it at contact stress locations. You can also have locations where there's changes in geometry. It could be a point load. A significant point load can cause a stress concentration, like a contact condition can cause that. Plates in tension or bending with holes, notches, steps. Those are things that can cause stress concentration. Shafts in tension, bending, torsion, holes, steps, keyways are just some examples. And other less obvious ones that I'll cover much later when I cover fatigue include rough surface finishes and external and internal cracks. Here's an example of an aircraft with square windows with no mitigation near those corners, and that was a significant problem. The Hollander aircraft, because you basically had stress concentrations at those corners that propagated and caused failure of the fuselage. And so we want to reduce those stress concentrations by using notches and circular type geometries. Here is a YouTube video that I'd like you to watch if you have the time, and it really goes into the theory in the background of elasticity in general. So what I'm covering there in this particular lecture is the constitutive relationships, the stress and the strain definitions, and how those equations play out together in solving elasticity problems. So very, very good and comprehensive um, video lecture that's going to give you additional background to this particular topic, which is stress concentrations. So I do want to cover two types of assumptions are made in the analysis of structures. One type of analysis is going to be a plane stress. So you can model things as 3D if you want to. In a lot of applications, plane stress or plane strain could be very helpful. A plane stress assumption, what it does, it helps you simplify the 3D assumptions so that you can simplify the problem, you can more quickly assess the structure. A lot of problems, you may be very surprised, but a lot of problems can be simplified to those plane strain or plane stress. It may be slightly more conservative, but or you can formulate the problem in such a way that's slightly more conservative. And the idea there is that it will simplify the amount of analysis you have to do by hand. Not by hand alone, but 3D. The first go ahead that we have is going 3D full blown, and that takes a lot of time. So, plane stress assumptions and plane strain assumptions. So, plane strain assumptions is such that you have a component that's very long in one direction. So, if it's long in very one direction, you can make some assumptions, and the assumptions typically are that sigma zz, which is along the length of the infinite direction or close to infinite, is zero, and then you also have tau xz and tau yz is zero. The stresses sigma x, sigma y, and sigma xy are only a function of xy, and those are the only ones that survive. I apologize because I did make an error. So what I intended to say is that this should be plane stress assumptions. I'm glad I caught it. Actually, no, this is, yeah, so plane stress assumptions. You have a body of material and it's relatively thin. And in this direction is z, and this way is x, this way is y. What you see here is that it's very thin in this direction. So sigma zz sigma xz and sigma yz have to be, they have to be close to zero because there's just not enough thickness for those stresses to develop. So that's a good assumption for plane stress. And so that shows up a lot. That shows up even in fuselages, where the thickness is fairly small compared to the fuselage two dimensions. So there's a thickness of the wall of the fuselage, and then this is the other two directions. So very good assumptions there that can be used, and I hope that's clear. Um, okay, for plane strain in a plane strain assumption condition, we're looking at um, so for plane strain assumptions, you're gonna have say a rod that's very long. Okay, so this direction you're gonna have a strain that shows up, but these other two strains will be zero, and we'll call this a plane strain assumptions. Okay, so that's fair enough. You can start with a 3D strain stress relationships, um, and the strain stress relationships in 3D can be used to kind of come up with what it will look like for a plane stress strain stress relationship. So because sigma zz, okay, so since these are zero for plane stress, we just go here into the constitutive law in 3D, and we plug in sigma z is zero, and we calculate epsilon x. For epsilon y, we plug in sigma z equals zero. For epsilon z, what we find is that that's non-zero because of the Poisson effect. You have a Poisson effect. That's why that's non-zero. Um, and then for the shear stress conditions, this will be zero because there is thin, right? So it's fairly thin, so it cannot develop a significant amount of shear stress in this plane. So that's what you get when you add equations 2a and 2b to get to the third equation. You can get this alternate form. This is what you will get. Okay. So two alternate forms to represent that. The equations of equilibrium for plane stress are given by this equation here. That's covered extensively in a different lecture. And these are the equations of elasticity right here. These are the equations of elasticity. And right here, what you see here are the body forces. And you may ask me, well, you didn't derive these equations. Yes, I did in part one. And I derived this constitutive law in part one. And to find those derivations, you can go here and check it out. So another equation that becomes very important is called the equation of compatibility. In other words, we have displacement compatibility across a whole body of material. And that equation actually becomes important because we actually use it to come up with this equation that you see here. And the fact is that for the body to be in equilibrium, you have to meet this compatibility condition. We call it kinematic compatibility, and it can be derived quite easily from looking at the strain compatibility equation. And if you never heard of the strain compatibility equation, the strain compatibility equation for plane stress, let me write it here in case you never seen it. It's a second derivative of respect to y plus second derivative with respect to x equals the second derivative of shear with respect to x and y. That's a strain compatibility equation, and it's a necessary condition for the body to be continuous and a whole body. It turns out that if I take these relationships and plug them in to here, you will then encounter this equation of compatibility, and that's why you see this Poisson ratio show up. And when I look at this equation, there's three independent unknowns in this equation. You have sigma x, sigma y, and you're gonna have also sigma xy is gonna show up. Here, fx and fy are the body forces like gravity or something like that. So that's equations, and it can be simplified to this equation. We can combine them. I can turn these equilibrium equations of elasticity, this in Cartesian coordinate system, Cartesian. I apologize if it's not legible. Let me try again, Cartesian. And I can take that equation and turn it from Cartesian, and I can turn to polar coordinate system. That has a great advantage when studying stress concentrations. And you may say, well, I jumped from motivation, right, straight into some equations, and you're wondering why. So the reason is because I'm going to derive the stress concentration factor for a circular hole. And to do that, I have to provide some background to that. Now, in real life, in industry, you're very unlikely to have to derive these equations to use the stress concentration factors. You can then open the stress works handbook or Bruns book or some other Peterson concentration handbook or stress concentration handbooks, and those the stress concentrations will be provided to you. But I think there's some benefit in understanding where the equations came from, because ultimately they can benefit you as you work through various problems. I'll discuss why that is. I think people that know where the equations come from can be a little bit more dangerous in using them to their advantage for complicated problems that may not be solved from the equations that already exist in a particular book. So, with that said, so I've turned the problem from a Cartesian coordinate system into a polar coordinate system, and this continues to the body forces. Now the difference here is I'm looking at a coordinate system that went from like that, x and y, Cartesian, to now what I have is r for radius, the radial coordinate system, and then theta, which is the circumferential coordinate system. So I can define any point by specifying x and y, but I can also do that by specifying the radius and at what angle theta, and I will get the same answer. And there's a direct correlation between the left and right? So we know that from mathematics that we can calculate that component as x equals r cosine theta, y equals r sine theta. So very important consideration there. I want to point out that that's how you'll arrive to the polar coordinate system equations, by using that formulation you will get here. The strain displacement relationships I show in this picture was in a Cartesian also. And we can convert that also into the strain deflection relationships that you see here. In plane stress, this is in the polar coordinate system, you're going to get this. In plane strain, you're going to get that. Here, this is a radial strain, this is a circumferential strain, and this is shear strain in the radial and theta plane. So yeah, that's very important to understand. So we can transform stresses. We can go from, if I know the stresses in the Cartesian coordinate system, I can use the idea of Mohr circle to convert that into into the polar coordinate system. This is the stress in the polar coordinate system, while these stresses will represent the stresses in the Cartesian coordinate system. That's very advantageous because if I can make that transformation happen, if I know sigma x, sigma y, tau x, y in the Cartesian sense, and I'm looking at how to transform that to the polar coordinate system, all I have to do is apply this formula, and that'll help me transfer from one coordinate system to another. If I want to do the inverse, go from polar to Cartesian, I can use this formula as well. This will prove very advantageous for what I'm going to do next. So let's examine a simpler problem, and this is a large thin plate which is subjected to uniform tensile loading, sigma naught at its ends. So we're going to be applying a uniform loading that's, and with a remote stress, we call that a remote stress of sigma naught at its ends. We want to determine the field of stress existing within the plate in polar coordinate systems. So now I look at the Cartesian coordinate system, and this is a polar coordinate system. And so I want to see how I can relate both. So I'll start, if I look here, and I know it looks very busy there, but let me draw it step by step. So here, what I've drawn is this. In the Cartesian sense, I have sigma xx. Here I have sigma yy. And then here I have sigma xy, sigma yx. Okay, that's in the Cartesian sense. But if I'm looking at the in the polar coordinate system, and please, if I'm now looking at the polar coordinate system, now I'm looking at a particular radius. I apologize, a particular radius here, r, with angle theta. So I'm really looking at the same material point. It's the same material point that can be represented this way or it can be represented this way. And so now sigma rr is, it looks like this. I'm sorry about that. That's an error. And now this is your sigma theta theta. And this becomes your sigma theta r. This becomes your sigma r theta. Okay. It's the same thing I have drawn here. It's just superimposed, so it looks very complex, but it's not. So we can use a Cartesian polar coordinate system. And the first thing I want you to notice is that we can first solve for the stress field in the Cartesian system. So in our example, notice how sigma xx coincides with sigma naught in direction. So they're in the same direction. So in the far field, this is true. Also in the far field, I want you to notice how sigma y, the stress in this direction, and the shear that could be happening on this plane is zero. We don't have that. So then I know that sigma y and tau xy are zero. So I can then apply the transformation equations are these ones. Plug in sigma naught here. This is zero. This is zero. So that's zero, that's zero, that's zero. And this is zero, but this is not. So in the polar coordinate system, this is what I get once I'm done doing that. So it looks very simplistic, but I did it. Notice how I did it for that plate without a hole, and there's no stress concentration. What I want to do now is study that problem, but with stress concentration. So before I do that, so I was just giving you a little opening. I'm going to go between practical and theoretical so you can stay engaged. But I just give you a little appetizer of what motivates a problem. What motivates a problem is you have this aircraft where it had square windows, and the crack initiated right there, right? And propagated. Multiple aircraft experienced that. And so at the time, those square windows got turned into a more elliptical style, right? Because now I don't have that stress, that sharp corner that's going to create a stress concentration there. So that's a study that we're having today, and I'll talk later about plasticity as well, because plasticity can help you assess that. And part of what we're going to be looking at is how we can do a plasticity problem with stress concentrations in such a manner you don't have to use finite elements every single time. You may have to, but for initial sizing, it could be sufficient to do hand calculations just to get started. So with that appetizer said, let's look at some examples of stress concentrations. Here you have an example of a gear teeth, and this right here is going to cause a stress concentration. You have a shaft keyway right there. That's a stress concentration in this corner. You have stress concentrations at bolt threads right there. You have stress concentrations at shaft shoulders right there. You also have a stress concentration at bolted or riveted joint right there. And then even in a welded joint where you can have multiple materials. I have seen failures due to stress concentrations in every single one of these situations. It's a common situation. Now, let's think about what's causing the stress disturbance. What is causing the stress concentration? What is causing the stress? If I apply a load in this direction, I think we can all agree that the stress concentration is likely to be the highest here. Maybe from experience you know that, or because it's intuitive. When I look at this, the reason that's happening is I like to look at stresses in a body as if it was a freeway. Okay, so say there is a freeway, and I'm traveling. These are cars traveling. These cars don't know there will be disturbance later, so they're traveling together. And suddenly, somebody with a truck in the 405 freeway drops a circular sofa, which, if you don't live in LA and you haven't come here, this is a common occurrence. Somebody will drop something big in the freeway, like a table or a sofa or something. So, once the cars approach the area, traffic slows down. And then guess what? Cars start to try to squeeze in. They try to get in, right? Maybe it slows down. But you're going to see higher concentration of traffic in this area compared to farther away where everything is moving at 70 miles an hour. Now maybe things are moving at 10 miles an hour. I like to look at stress concentrations in terms of traffic patterns, and I call this load path diagram. Load path is very helpful in understanding what is going on. Uh, for example, let's say you have a truss system, and this is fairly thick truss, but this one here is a very thin truss, and this is almost like a string. Well, if I apply a load, my load path is going to look like, oh, there'll be a lot of load going here, very little load going here, and almost no load going here. So you know what a load path looks like when you're designing. It's good to have that idea. Even in a complicated problem, spacecraft even, I encourage you to think about a load path in terms of load path. So here the hole is causing a stress concentration, and we were looking in terms of load path here, and I use a traffic analogy. When I'm looking at a particular problem like this, um, what I intend to say when I say far field, so far field stress applied stress is equivalent to stating stress applied remotely, meaning is applied far away from the area of interest. In the case I was studying earlier of a plate with a circular hole, when I say far field stress, I'm talking about remote stress, a load applied far away from the region of interest. Okay, almost all the problems can be broken down in this manner. So let's consider now a plane stress. We can look at a plane stress problem here, and we have this circular hole on a plate, and I'm considering here the angle theta, And the radius R naught is right here. So this R naught. And R is a particular value away from that center of the hole. The closed form solution actually looks quite simple compared to one we'll have expected. So the formula is actually given here. Sigma R here is a radial stress. Okay, that's a radial stress in that direction. While sigma theta, as an example, is a stress in this direction. And believe it or not, there's a component of shear that's in that plane of r and theta. That's a little bit hard to draw because it's better to draw, it would have been better if I drew a square pointed over here. So that point is this point. And then I can draw everything nicely. Sigma r, sigma theta theta, sigma theta r, sigma r theta. Okay, so that is a formula, and I'll show you later how that's derived. I think it's important to understand where things come from. And let's look here very carefully. Okay, let's look first. This is stress applied remotely or far field, and I want to look at the stress right at the hole, but here, say as an example. But sigma RR. Let's see what's going on with sigma RR. So that's going to be a theta of, say, theta is 0 there. So this is going to be 1. R naught, R is equal to R naught right at the hole. So this is 1. This is 1. So this whole thing becomes 0 in this parenthesis. And this is actually 0 as well. So sigma RR at that location is 0. Okay? At that location, 0. So that's quite interesting that that happened. Why we don't now examine carefully what is going on, and I'm going to try to clean this up so we're not getting confused. Let's look at what's going on there, but in this direction, which is sigma theta theta. Okay, at that location, uh, we can plug in what theta is. Theta is 0 at that location, and R at that location is R naught. So let's look at what's going on here. So sine of 2 theta, so that's 0 here. So the shear is 0. There's no shear. Okay, makes sense. This is 1. This is 4. This is 2. 2 minus 4 is 2. 2 divided by 2 is minus s. That's actually quite interesting. That's actually kind of weird if you think about it. Let's think about that again. So I'm applying a load, remote stress S, in this direction, tension, but I'm developing this loading here in that direction that's in compression. So it's pushing in, right? And the amount that's pushing is actually negative S, which is the same amount as what you see there. That's actually a very interesting finding, okay? And one could say is probably unexpected for some people that that's the case. Potentially true. Um, let's look at the situation of a stress R here, but I want to look at sigma RR, which is this way. So to do that, let's examine R equals twice R naught this time. So let's see what happens there. Cosine theta is 1. Theta is 0, so cosine of 0 is 1. R naught divided by R in this case is, well, this is going to cost more work because of fractions, but R naught divided by R is 1/4, so this becomes minus 1. This becomes 3/4, and this is 1. So this whole thing becomes 3/4. So I get S half, I'm sorry. So I get 1 minus 1/4 plus 3/4. Yeah, so I get 3/2 S. Hopefully that's correct. I was moving fairly quick there. Um, I'm checking. Yeah, it looks correct. So again, it's intention that way, but it's and look at how the stress increased there. Um, and then you can take these numbers to infinity. So let's see when I take this to infinity. So when theta is 0, that becomes 1. When r goes, when r over is close to 0 because it's close to infinity, I'm going really far away. So r is very large compared to r naught. This is 0, that's 0, 1 there, um, this 0. So 1 plus 1 is 2. I get s over 2 times 2, that's s. And that makes sense. That matches the load applied. So you can see the boundary conditions do work out very nicely. The far field stress is getting correctly put in. But now let's look at the stress concentration. Where is the highest portion? Where is the highest where this occurs? And you could actually determine that location very simply by the way to do that is to take the derivative of sigma RR respect to theta at r equals r naught. And when you do take that derivative, you can set that equal to 0. I apologize for that. And that the theta is going to come out is at pi a half, which means that I'm looking at the highest stress concentration or the highest stress I will get is probably going to be, and I'm sorry, you're going to find that sigma theta theta is the right number. I'm sorry, sigma theta theta is going to be here in this direction, which is sigma theta theta. And that location is at a theta of pi a half or 90 degrees. And when you do the calculation, what you find is that you get that the stress at this location is 3 times S. So stress concentration factor um, is going to be 3. So in other words, I apply a far field stress of S, and then near the hole, that stress concentration becomes 3 times. And you're going to see that in the modeling that you'll be doing as part of this class. So very interesting stuff. And one question that's quite interesting is, at what theta will we have sigma theta equal to 0? That's a very interesting question that one could try to answer. Um, that we won't answer here, but it is a good question to ask yourselves. Is there a condition for which sigma theta theta is 0, right? Because I went from minus S, I went from minus S to 3 times S that way, as theta was moving from here to here, right? So there must be a location where sigma theta theta is 0. Now, that's a theoretical question, not that relevant, but it's an interesting question to ask. So if I consider a large thin plate containing a small hole of radius A subject to remote simple tension, what you're going to find, and I'm showing the formula here again. This is the same formula as the one shown here, uh, but here R naught is A is what is being used. The main point of showing you this is so you can see how the stress drops off from the stress concentration. So it drops off from the hole quite quickly to the edge, and it will drop um, fairly significantly quick. And you can do that plot to understand it better how quickly it drops off. So that's something very, very important to point out as you work through this. The stress concentration is highly localized, and it can be looked at from this perspective as well. Like you can plot the stress uh, in the manner I just plotted it here. So sigma theta, theta is the highest here, smaller here, smaller here, smaller here. So really what you're plotting here is really R, basically R, right? Going back now, okay, now that you know the equations for this, now the question is where they come from, right? It looks mysterious, and I think there's some good points of looking at this, um, of where do they come from. So yeah, these are very interesting equations. So let's look at that. So the first thing I want to point out is that we have these stress strain relationships that we talked about earlier. These are the same ones I discussed before for the plane stress conditions. Um, and some of you may ask me, where did this come from? You can derive them very quickly using some quick experimental conditions. It's not very hard to do. So I'll do it really quick so to demonstrate. So if I have a little structure and I apply a load here, right, P, there'll be some axial and there'll be some amount of there'll be some contraction due to Poisson ratio. So if I apply a load, for example, let me do in terms of stress. So if I apply sigma 1 in this direction, then I'll get some sigma 2 going. I'm sorry. I apologize again. Okay. Let me just draw this again. So sigma 1. I apply sigma 1. That produces a epsilon 1 in this direction. And we know that the epsilon 1 is going to be sigma 1 divided by E. It's going to cause a Poisson ratio effect of sigma minus nu epsilon 1, which is minus nu sigma 1 over E. Okay, so we know that. And finally, once I know that, I can now do another experiment with the same part and apply sigma 2 in that direction instead. And when I superimpose both, I will get the fact that the strain can be superimposed so it looks like this. So if I did the experiment now in reverse, I'll get epsilon 2 to be sigma 2 divided by E. And I'll get strain 1 equals minus nu epsilon 2. And now I can add this epsilon 1 to this epsilon 1, this epsilon 2 to this epsilon 2, and I'll arrive and I can switch 1 and 2 to get epsilon 2. I'll arrive to this same equation you see there. So you can actually derive these equations just by doing simple experiments that are not that hard to do. I can invert the stress strain relationships to get this. This is obvious. You guys have seen this. This is the shear modulus right there, half of it. So yeah, you get these equations, and then you can you put into the compatibility equations, and you get this equation now. So give me a minute here. Continuing on here, we have this equation here. Again, these are the body forces, which we could set as 0 for this example, since we're looking at the problem of a circular hole with far field stresses, right? So no body forces need to be considered right now for this example. So if I were to write the equilibrium equations, I will have this equation, and these equations. And you say, man, well, where did these equations come from? We had them earlier. So these first two equations are the equations of equilibrium in the polar coordinate system. So let me show you that again so you remember that we covered it. Yeah, there you go. These are the equilibrium equations in the polar coordinate system. You can see they are there, right? So that's the same thing we discussed before. We are setting the body forces to 0 for this example. And then we have the third equation, which we're using, which is this one. Huh? Right here. So, so I have three equations here. The first equation is a equilibrium equation. The second is a equilibrium equation, which are the same thing I showed in the previous page, in the previous pages below, before. And then I have this last equation, which is exactly what I have here, but written in more compact form. And you may not be familiar with that, but all you're doing is you're operating this stress, there, you're operating this stress there. What we call this an operator, okay? Um, this right here is an operator. Okay, so what we're going to do is we're going to come up with a way of solving this faster because we have three equilibrium equations and we have three unknowns, sigma RR, sigma R phi, sigma phi phi. And I need to somehow solve it for this plate in the whole problem. What I'm going to do, I'm going to use the idea, and we call this a stress function. It's a stress function selected in such a way that somehow you can satisfy all three equations exactly. And that's a neat part about the Aries stress function. You select these functions in a way that when you plug this in, and you don't know phi. In this example, you don't know this big phi. This big phi is what is unknown. But R is a radial coordinate system. And the idea here is when I plug in these stresses, and you can do it in the comfort of your home. If you plug in these three equations, um, if you plug in these three equations here, you will see that the three equations will come out to be 0. So this is an excellent choice for these stress functions. The phi is the one that we don't know about. We're calling that the Aries stress function. That's what we're calling that. Okay, so that's the idea is let's figure out, can we find this phi such that when I plug in the stress functions into the equilibrium equations, I get exactly 0. Now, the right answer is yes, I'll get 0. So I encourage you to try it so you can see that that actually does happen. Okay, so when I do that, when I plug in these equations into particularly this one here, you'll get something called the Bar Harmonic equation. It's going to be a fourth order equation, partial differential equation, and it's going to, and I'm telling you, it looks crazy that's going to happen, but if you were to plug this in here, that's what you will get, guaranteed. In this biharmonic equation, the good news is there is a general solution to this equation. And the general solution can be broken up by using separation of variables. So we can start with an infinite series sum from n equals 0 to infinity. And we can break it up into the radial coordinates, a function f g sub n that depends on r, and an expansion on phi, which is, remember, in our situation phi, I was using theta earlier, but I changed the convention, so r and phi, okay? Now this phi is not the same as this phi. This is the function that we need to find, because if I know that function phi, I can plug it in here and I can actually find the stress field for the problem of interest. I hope that's making sense right now, and I really encourage you to kind of pause and think. Okay, so I think it's fairly simple. These are equations that govern the elasticity um, equations of elasticity. To summarize one more time, there's nothing strange going on here. These are the equilibrium equations. This is a compatibility equation. And all we're saying is that if I plug in the stress, if I use this Aries stress function in such a way, and I come up with the sigma RR and come up with the sigma phi phi, come up with sigma R phi, I can exactly satisfy these first two, and the very last one looks nice. It just looks like this. It comes out to be the Bar Harmonic equation. And we know that the general solution of the Bar Harmonic equation is simply an infinite sum series of um, this term and then that term multiply, where this term is talking about the function in this direction, and this one here is talking about the behavior in that direction. So we can substitute this general solution into the biharmonic equation. And very surprisingly, when you go through the math, you will find that this equation we get. Now, what is the beauty of this? The beauty of this is that we got rid of these fees here, right? That fee is not showing up now. So now I have a single equation that only depends on n. And now I can, and this is an operator that's applied on G. And so in essence, I have to just find these G's. Now, that's an ordinary differential equation. So now I've converted a partial differential equation. This is a partial differential equation. I've converted that into an ordinary differential equation very nicely. Now, I don't have to do it by hand. The good news is that we know that the solution to this differential equation, and you can use Mathematica or MATLAB or some code. I don't particularly care. You can open a book that has it or try to do by hand. Bottom line, I'm just giving you the answer, is that the solution of differential equation can be written like that. Um, when n equals 0, because remember that series starts at n equals 0, the differential equation, the solution to this differential equation is simply going to look like this one here. So you can see the first, yeah, so that's what you get for that one. For n equals 1, you get this one. And for n greater than 1, this is the solution. So unfortunately, unfortunately, when you expand this solution, it's going to depend on G naught G1 for sure, but then it also depends on Gn, and n can be greater than 1. But at least for n equals greater than 1, the solution always will follow this formula here. So at least we have that. Now, what I'm going to do next, so I don't want anybody to lose the perspective. I'm trying to solve the problem of a hole on a plate. I gave you the solution, but I want to tell you where the solution comes from so you at least know where it comes from. And it comes from the equilibrium equations. The Aries stress function satisfies the first two exactly. The third one is the compatibility equations, that which is telling us that the body is continuous and it's not breaking apart. And then if I were to plug in this guy, these three there, um, then I get the Bar Harmonic equation. The Bar Harmonic equation has a general solution. The partial differential equation turns into ordinary differential equation, which has three solutions you see here. Um, uh, but not three solutions you see here, but for each value of n, you have a solution here at the bottom. So the next step is to look one by one. So at n equals 0, what is going on? For n equals 1, what is going on, and so forth. So you can go in and actually look at what is going on for n equals 0. And for n equals 0, you get this. So all I'm doing is taking the solution for, I'm taking this solution here, and plugging that solution into sigma RR, for example. So if I do that, I get that sigma RR will be that. Sigma phi phi will be that. And then I can calculate the deflections if I wanted to. UR and U phi is going to look complicated. But that's fine. Sigma R phi is 0 for this problem, for this particular solution. At n equals 1, now you have a sigma RR, sigma phi phi, and sigma R phi. And again, what we're doing is taking this solution here of sigma 1R, G1R, that solution there, we plug it in to here to get what that should be. And you have a cosine phi, sine phi there. That makes sense. And that's coming from the first term. The first term here for n equals 1 is going to be cosine phi, sine phi. And this is going to turn into something simpler, which is cosine phi times sine phi. So I won't go into the derivation for that, but this is what you get. You can also look at the deflections and find them. Because once you know stresses, you can get strains. Once you know strains, you can calculate deflections. But this is what you get for n equals 1. For n equals greater than 1, there's 3 stress components look like this. And you can see here how you have cosine n phi, sine n phi. So again, it's a summation in series. It's a series summation. So I need to get G1, G naught, G1, G2, and this is a summation. So I need to get each of those, and what you're doing is plugging them here to see what's going on. And then add them up at the end. So for n equals greater than 1, this is what you get. I encourage you to, kind of do it to see if you can get the same answer as what we got here. But I don't want to spend too much time. We'll cut to the chase. So if we consider a plate subject to a particular load, remote load sigma naught, if this circular hole of radius A is made very small compared to the plate, uh, I think you will know that this distance is irrelevant, right? Because if this applied really far away, who cares? So the state of remote applies stress in Cartesian and polar coordinate systems. In the Cartesian system is going to be this, but when I look at the polar coordinate system, what I realize is that at theta equals phi, so if I look at an arbitrary angle theta, um, I can use the transformation equations here to figure stuff out. So I can use the transformation equations. I know sigma xx is sigma naught. I know sigma yy and sigma xy is 0. I can use the transformation equations to transform it. And in this problem, I'm trying to convert sigma. I want to convert this. I want to find these guys in the polar coordinate system. I already talked about how to do that transformation, so we don't have to go too crazy on that. And I showed you already that that transformation is just this for the remote stress. The remote stress is all you get. Very simple there. And so now, as r tends to infinity, uh, we know that this is what I need to get, right? So that implies that the stress function has to be of this form. Because I know the solution for phi. The solution for phi is adding these ones like this. Okay. I have to add them anyway. So I know what it needs to be already because it needs to satisfy the far field conditions. And so when you examine the terms very carefully, what ends up happening is that you find that because the the stress components I just showed earlier, they have to be equal to this. That means that my Aries stress function has to be of this form. It can't have cosine 3 phi and stuff like that. It cannot have the other higher order terms. It just can't have it. Um, we also know from the solution that we shouldn't have cosine phi plus bn sine phi. I know that because when I look and examine these terms, I don't see that term separated like that. So that tells me that I'm good to go with just considering these two terms alone. Okay, so basically, looking back, considering just n equals 0 and n equals 2. So I don't have to look at an infinite series for this particular problem. So once I have that, I can now examine further. And then from the equations I had before, if I want to just focus on these ones, what I find is that these are the general forms I need to consider. For n equals 2, this is what I get. As r tends to infinity, I need to get this. And so that implies that for n equals 2, this is what I get. Yeah, I just copy and pasted this over here. But this, as r goes to infinity, I need to get to this somehow. And so then I can start working it through. For r, n equals 0, I know what that looks like. For n equals 2, I know what that looks like. And so noting that the stress must be infinite as r tends to infinity, you have to have b naught and a2 equals 0 for this to work out. So it's just the only way to make that work. Um, and I'm here that b naught is this one. And a2 is this one. So yeah, that's the only way for it to work. For the stress to be finite as r goes to infinity, that's the only way to make it work. And as r tends to infinity, you can actually reduce the equations even further. Um, at r equals a, which is right at the hole, so right at the hole, we also know sigma r is 0, because right at the hole, I shouldn't have a stress right here in this direction. Why? Because if I look at a point right there, this is a free edge. So that stress is 0. And then the shear right on that free edge, the shear load, shear stress there, also has to be 0. So I can apply those two conditions as well. And when I go through that, actually I can find all the different coefficients I didn't know about. And that's amazing because once you do that, you solve for A naught, D naught, B2, D2, C2. I already know B naught and A2 because the stress has to be finite, and the only way to make it finite is to set this equal to 0. What we find then is that this is the solution to a plate with a hole. Has to be, there's no other way. And that's amazing. That we've done something pretty incredible. And the solution for the stress states at um, r equals a in this example, I'm using a as the radius of the circle, is just basically this. So I know there was a lot there, a lot of mathematics, but let me just summarize one more time so you can see the big picture perspective. We took the equations of equilibrium, which are here. We selected an Aries stress a function that I don't know what it is, but I've came up with a form that when I plug it in here, I get exactly 0. And then the third equation turned into Bar Harmonic equation, which we know the general solution for. We can substitute it to get a governing equation, and I know how to solve that ordinary governing equation. And for each value of n0 n equals 1 has very specific solutions. For n greater than 1, you have more general solution you can get. Um, and then from there, I apply the boundary conditions of the problem for a circular hole. And I basically showed that phi should only have these two terms, cannot have other terms, because we don't have, you can see it here, we don't have cosine 3 phi or anything like that. So it only has these terms. And we know this, because I know this, I will just select the solution for this, I can then plug it into my stress solution, which is right here. I can apply the boundary conditions, the remote stresses. We know that the stress has to be finite as I go farther and farther from the hole. And if I go to infinity, obviously R goes, if R goes to infinity, sigma goes to infinity. So A naught, A2 has to be zero. That's the only way. B naught is another one. As R goes more and more to infinity, sigma phi will go to infinity. So that has to make that equal to zero. So those make sense. Then I apply the boundary conditions right at the hole, which I know this needs to be equal to zero. And when I do that, I can solve specifically for all these coefficients I didn't know, which I think is amazing. Once I know that, I can plug it back in, and I'm able to get the stress components right at the hole. So with that said, I want you to think about that. So this takes us back to considering a large thin plane containing a hole. The small hole of radius A is shown. You have a far field stress, sigma naught, and you can then use these formulas to calculate how that stress varies across the whole thing. You can see here what is going on with the stress. The sigma theta theta particularly is very interesting. You can see how it goes negative here at theta equals zero, and how it turns into positive, but even amplified 3 times to a very high number. And that stress is the one going that way, tangential to the circle, right? Is negative and then turns positive. And you can see here there's a point in time where it crosses zero. You know, it's not a big deal that crosses zero, but it's kind of interesting that that happens. But that is a stress. And that's when you have a stress applied in this direction. That's the stress acting here and here. Okay, that's actually very interesting. I can now complicate the problem further. Okay. And I can say, okay, what happens? Do I need to rederive the equations? So the equations I was showing earlier are for uniaxial loading. But what happens if now I have to look at this situation? How do I deal with that? Right? Well, it becomes more complicated, but not undoable. In this case, you see a stress state. So I know. So let's look at case one. I have this case. So sigma, I'm going to look at sigma theta only, sigma theta theta. So which is tangential to the circle. So when I say tangential, what I mean is if this is a hole, it's always like this. We already know that at the hole, we already know at the hole, sigma r is zero, has to be zero, and sigma r theta, I apologize. But we know sigma theta theta is not zero necessarily around the hole. And so if I look at this case, I know the stress here is 3 times sigma naught. The stress here is negative sigma naught. But now, what if I want to, what if I want to go ahead and now look at this case, case two? I've applied load this way, and that's a hole. Well, at this point, I get negative sigma naught. At this point, I get 3 sigma naught. So what I can do now, I can do superposition. I can, if I want to look at the case of um, this case, I can add these two cases. And what I notice here is that it's actually kind of counterintuitive. It's not clear why this happens, but I'll explain why it happens. You can see that 3 sigma naught plus minus sigma naught gives me 2 sigma naught here. That minus sigma naught and 3 sigma naught give me 2 sigma naught here. So I'm actually getting 2 sigma naught when I add these two together, which is counterintuitive, right? Because I'm applying stress now in two directions, in tension, yet the stress concentration went down. And the reason for that is because in one case, the uniaxial case, if this is a hole, when I apply the far field stress, the hole elongates. And that's the poorly drawn ellipse. And that's where the high stress is. But when I apply in the biaxial case, you're almost like uniformly making this circle bigger. So you have a stress concentration, but it's not as dramatic as if it was uniaxial, which that's why understanding the theory is so good, because then you can use superposition to your advantage because you understand the equations well. And that's why I was going through that, so you can follow it. So that's very neat. If I have the case where I apply compression, now this is very counterintuitive. If I apply compression this way, then I have intention this way, the stress concentration goes higher, goes to four times sigma naught. Because now, for case one, I still have the same thing. And for case two, now I'm applying compression. So this stress here now becomes positive. So 3 sigma naught plus sigma naught gives me 4 sigma naught. Okay? I can go even, I can get even more dangerous. I can say, okay, the load applied here is sigma A, and the load applied here is sigma B, and I can apply superposition. The answer is going to be that at this location, the stress state will be 3 sigma A minus sigma B at that location. And finite elements should be able to replicate that behavior. And I already explained this case, right? So here sigma A and sigma B sigma naught, so I get 2 sigma naught. In this case, I get the same thing, it's the same formula, 3 sigma A minus sigma B, but sigma A sigma naught, sigma B is minus sigma naught, so I get 4 sigma naught. You can see that there. The highest stress is right here. Makes sense. What if I have a situation where the stress components near a circular hole on the remote uniaxial tension were given, but we want to find the stress components near the hole for remote pure shear stress? So that's interesting. Now I have this situation where I'm applying a pure shear. Okay. Okay. So I just want to apply shear, and I want to know now how to solve it. So there are ways to do that. Our problem is this one, but I have solution for this one. So we need to transform our problem definition to a format we can solve for. So we can use the plane stress transformation equations again. And what you find for a pure shear stress state, this will give you the answer. Um, it's going to give you the solution for this. It's going to be basically biaxial, which I already looked at before, um, and it's at a 45-degree angle. So I know the principal stresses, and that's equivalent to this situation. So a state of pure shear can be transformed into a problem like this. So in general, then I can take superposition again. I can then solve. Uh, I know the stress state for this one here, for this situation here. I know the stress state for this situation here. And then I can go ahead and use the same formulas I had before and solve them and take advantage of the fact that I can use superposition. Um, so this is what you will get after you're done. The remote stresses, um, sorry, the stresses near the hole due to remote shear stress are given here. This is what you will find when you do it. And that's by using superposition. And of course, here we're looking right at the hole or away from the hole. That will also, these equations will also work. So this is very exciting that you can do this kind of thing fairly quickly. The example problem here given is that for tau infinity, if I have tau infinity going that way, right at the hole, um, right? So then I have what? I have 300% increase in that. We know that is negative tau infinity there. Here is in compression. So I get negative 300% here, negative 100% here. And I can then go ahead and superimpose them and I'll get 400% here, minus 400% here. And they're going to occur at a 45-degree angle, which makes total sense to me. So for a more general loading situation, if you were to have a general loading situation where I have a stress state sigma YY far field, sigma XX far field, a shear far field, the formulas given here work for any of those situations. That's the beauty of that. I can use the transformation equations and I can get the stress field at any point around the circle for that situation. That's amazing because a lot of people look at a book and they just see this formula. But what if we have this situation where the load is applied here, here, shear, and this may not be the same. This may not be the same as this one in magnitude. Well, I have the formula here, and we can use it very successfully. And I encourage you to always look for those solutions because they may help you save time. You may not have to do even finite elements for those situations. So I already covered the stress concentration idea, the stress trajectory idea, where uh, this one may be less perceptive to what's going on here. The ones near the hole, they will have to like accommodate that hole, and so you're gonna get a higher stress over here because of that. So I covered that already. The theoretical stress concentration factor, KT sigma max, this sigma max here, divided by sigma naught. And you can actually measure this stress concentration and prove that it actually does work. Photoelasticity is one approach that people use. You can use a plane of polarized light. You will pass it through a photoelastic material, which will result in a colorful fringe pattern, and that will indicate the intensity of the stress. And people have done that in gears. You can see here a stress gradient there, really providing information that there's something going on there near that hole. Here's another example of the stress gradient occurring there across this direction. And here you have a dog bone with a notch, and you can see here the stress concentration there's over here as well. So let's look at comparison for elastic testing with analysis. So here we have, so let's look at this example. This is a worthwhile example to look at. we have a loaded plate under tension. The remote stress is 320 psi. Um, the radius is 2r and the diameter d. So we want to look at what is going on here. So here is 320. That's a stress. Uh, the stress, for example, at BB, yeah, so we want to find out what the nominal stress is here at this particular location. Um, that stress there is sigma naught. So I have this load applied far field. Now this is a finite width problem. A finite width problem, you can actually find the stress, the average stress. So that's all we're trying to do is find the average stress there. So this is D. Um, and this distance here, this plus this is D minus 2R. And that's D from here to here. So I know this 1.5 is given to us. The radius is 0.5, the diameter is 0.5. So I get 480 psi. So applying, with not even accounting for the stress concentration, there's nothing to do with stress concentration. If I apply 320 psi far field, just because I have a hole now, the average stress across this wall is 480. And I can find that by calculating the area, right? This area here versus this area here, right? You have to scale it up, right? So you get 480 psi. From photoelasticity was found, using photoelasticity was found that in this zone I get 320. That in this point here we get 280, and then right at the hole we get 1130. That was found through testing and photoelasticity. Right here, 130. Right here, 280. Right here, 320. So for elasticity, first of all, I was able to confirm that the load applied 320 got transferred correctly to a point here, but I did get a stress concentration. Now, from analysis, you can use you can use a formula that's available in stress works. Now, I said earlier how the stress concentration is 3 times the remote stress, but that's for infinite width plate. For infinite width plate. Now that we have a finite width plate, the stress works handbook can provide you a correction for that. You don't have to worry for that. There's formulas for that. And I know R, so I know the radius of this circle. I know D, the width of this plate, so I can plug it in here, the numbers. And when I do that, I get that I get 2.31 as a stress concentration factor due to that. While using photoelasticity, I got 2.35. So yeah, so I take the 1130 divided by 480, right? So that's 1130 at this point, and then divided by 480 will be 2.35. That's a that's an increase due to having the hole there. That makes sense. I'm taking the max stress that occurs divided by the average stress across that cross section. And that's what that was done, 2.35. And we've done that analytically as well and find 2.31. So very close from each other, the solution. If we go back to this problem here, so if I look this again now a little more carefully, that width is W here, and this diameter D of that circle. Now I'm using different convention from here, but that's because this comes from a different book, like Shigley. Um, let's examine that. So if you have a very small hole compared to the width, which means that the width is almost infinite. So the width goes to infinity. It should approach the solution I had derived earlier, which is 3, a factor stress concentration factor of 3. And you can see here I get 3 because d over w will be close to 0. So at d over w of 0, I get 3, which is what I had derived. But once you have finite width, that's going to drop, right? Um, to even 2, can drop quite a bit. Um, you can also look at different situations. Like say now we have a plate, but you apply bending. You're going to get a stress concentration. That should happen here in tension, here in compression. Well, the stress concentration factors are provided here for, um, and you can see here that this is going to depend on two parameters, d over w, which is the diameter of the hole compared to the width, but also depends on the thickness. So d over h. So this d over this h. And yeah, you can see here that it depends on that. And that the greater h is compared to d, the greater h is compared to d, the stress concentration factor increases. So in other words, the thicker it is, the higher the stress concentration factor. But there's a point at which if h was extremely small compared to d, it will asymptote to this one right here. Very nice. You can also look at stress concentration factors for um, a plate with notches, like the ones you see here. And you can see here that again, this is R over D. So these R here compared to this D. If D was extremely large compared to R, then it will approach high. If D was very large compared to R, and D here is not the diameter anymore, is this width here compared to the radius of this notch, then the stress concentration will increase as that's occurring. But now you also have the effect of W over D, which is shown here. So several things to consider here in these plots. Then you can apply bending to this instead of actually, you can actually apply bending, and then you get these plots as well for stress concentration. And then here's the stress concentration for the case of when you have a notch here. And that R over D, that's R over D here. And then you have this D over D, it needs to be considered as well. That ratio matters. They have shafts, and I've seen failures that occur in shafts, so that's very important for us to really understand the stress concentrations. A lot of people create very sophisticated finite element analyses when in some cases all you have to use is a handbook formula as what you see here. And what you see here is a shaft that's loaded, is cylindrical in nature. Um, and again, it depends on the R over D and D over D as well. And that'll give you a stress concentration factor as well. Then torsion. Torsion is going to have a stress concentration factor. A lot of people don't realize that you have one, but you do have one for those scenarios. And the polar moment of inertia comes into play. And this you're going to see a lot in shafts, in engines, and things that are rotating. That's where you're going to see this. And you're going to see these transitions that occur that need to be considered. And I see often they're not considered carefully. Bending moment now on the shaft, you're gonna see that when you have misalignment on a torsion on a shaft that's rotating. If there's some misalignment, you will start getting some bending as well. And feel free to pause and check it out. These are also in Shigley's handbook. Then you have the idea of a keyhole on a shaft, and you can see here the hole through that shaft. And you also get a stress concentration, and it can be quite high. and the highest stress concentration will occur. You can have the highest stress concentration at point B and A. B where it inters A where and B where it intersects that edge, that free edge there. Again, bending moment applied also causes stress concentration. This for torsion, bending, and here you can see the formulas used for sigma naught, MC over I. You guys have seen that bending moment times C divided by moment of inertia, second moment of inertia. Here's the formula for sigma naught. Again, MC over I type calculation. Pin loaded, you're gonna see that a lot, where pin is loading a plate. Um, that's going to cause a stress concentration factor. And look at how high it can get. It can go beyond 3 in a lot of cases, depending upon the situation you have. Um, the larger W is compared to H, um, they're more likely going to have a higher stress concentration. That's generally the case. The larger D over W is, so meaning the larger W, the larger W is, the width is compared to the diameter of the pen. So you're going to then also increase the stress concentration. And that makes a lot of sense. And if you have any kind of clearance, so say you have a hole and it's pin loaded, and then you have the pin there and there's clearance, expect to increase the stress concentration another 35 to 50%. And that's very well known that that could happen. Here's a journal paper that discusses those findings. Here's a stress concentration for scenario of a grooved round bar in tension. Here is the same scenario, but now in torsion. So this is in tension, this is in torsion. And then here's another example of stress concentrations for looking at and the approximate stress concentration factor for bending of a round bar or tube with a transverse round hole. So you have this hole going right through it. So again, these are closed form solutions in tables and curves that can be borrowed. And that came from the Peterson Stress Concentration Handbook. Um, that's very well and widely used in our area of expertise. I recommend that you buy the Peterson's Handbook or the book Stress Concentration Factors, and also see if you can get the Shigley's book, which has a lot of these formulas. And then with Stress Works, you'll be complete. Here's even more examples. Now you're looking at bending moment applied to a scenario where there's this notch shaped in there. And again, these curves depend on a lot of different parameters. In this case, depends on R over D. You can see here, we're looking at stress concentration right at point B here. And so here is giving you KTB, which depends on R over D. Notice how it depends just on R over D. That's it. That's it. At location A, you're looking at 1.6 with these assumptions, right? More stress concentration formulas. And it compares without key, with key. And then there's interaction equations when you have torsion and bending moment applied. So these are bending only, these are torsion only. And then you'll find formulas where if you're somewhere in between, you can see that here. This is just torsion, torsion of moment is 0 here. here a moment, bending torsion 0 here. And then if you're somewhere in between, there's interaction equation for stress concentrations. What if you have elliptical stress concentrations? Elliptical holes. The stress concentration factors can get even more dramatic. And I won't derive the equations today, but in essence, it's very similar approach. Is tackled using elliptical holes, using elliptical coordinate systems now, which complicates matters a little bit, but it's still doable. It's still it's still doable. And the stress components for a situation like that is are going to be given by this formula here. You see it there. Sigma alpha alpha plus sigma beta beta. Um, and the formulas are given here. The max stress will be at beta equals 0. Um, so yeah, again, we're using elliptical coordinate systems here. Beta equals 0 in this scenario is over here. So we're going around the hole. Um, and the max stress is a beta equals 0 if the stress is oriented that way. It's going to be right in that location. And the high stress will be in this direction. And that stress is going to look like this. Stress equals 1 plus 2a over b. Now, if it was a circle, a equals b, so you'll get a circle. So 1 plus 2 is 3. I recover what I had for a circle, okay? The stress components can be found through these formulas here. So what if I have this scenario? Uh, so yeah, here's the formula for that. I have this circle, ellipse, stress concentration. The peak stress is this formula. Some people write this formula as rho equals b squared over a. So you sometimes you will see a squared of a over rho. Is fine. Rho is a tip radius basically, the radius of curvature basically. Like if I can draw a circle here, if I can draw a circle here, that's what that rho is. That's what people have used in the past. Um, and that circle needs to be within this ellipse. So what's the greatest circle that goes through this point that's within this ellipse? And that rho is your basically radius of curvature. As the radius of curvature goes to infinity, these terms goes to 0, and the stress peak is just S, right? When rho is near A, this rho is near this radius of this distance, then equals rho equals makes this 3. So again, if I have a circle, I recover it. And so that's the stress concentration factor for an ellipse. What if I have the situation of biaxial loading? So I have loading going this way, loading going that way, and this is S, this is beta S. And now I'm using beta, uh, not the same beta as this beta that I was using here. So here I was using beta for the angle around this, where I'm looking at in the coordinate system in this direction, in the elliptical coordinate system. But now I'm using beta for something called the biaxiality ratio. So I'm applying a load in this direction, a load in this direction, in this wall. If beta is 1, the load applied here and the load applied here are equal. So it's a biaxial loading configuration. If you have an elliptical hole, then the stress formula is going to be given by these values that you see here. So if you were to have a thin-walled pressure vessel under pressure, beta will be 0.5. We know that. And so for the case of a circular hole, A equals B, SA, the loading here, will be 2.5 S, and the loading here will be 0.5 S, which is lower than a 3S for uniaxial loading. Same case, but elliptical hole with B over A equals 2. You can see that the stress concentration factor has decreased to 1.5. So if I have a square hole, so I have a square hole here, which is a dashed line with rounded corners, just rounded corners here. Um, with R being 10% of the whole width, right? So the radius of that little corner here is 10% of the whole width. The stress concentration factor is 4.04. So this is very applicable to aircraft application, where you could have this square, this uh, rounded corner. Pin loaded, I already covered that. Lugs are fatigue critical. And also you could get fretting corrosion. I already covered that point, but here's another curve you can look at um, for design. And notice how open hole alone with no pin is a lower stress concentration factor than if you have a pin loading that hole. So moving on, this comes straight from the Stress Works Handbook. And what you're going to see there is, and I don't want to go through this because you can download this book, get it through the library or the at work. And what it's very nice because it provides stress concentration factors for a variety of problems. Here you can see one such problem, and it's very neat how you can actually go through and really solve for a lot of different problems. And it shows you how the outer corners look like for various scenarios: square, rounded to radius, square, and things like that. So very very useful. Here you can see a plate with multiple holes, and this is very nice. It gives us the stress concentration factors for those scenarios. Four holes are near each other. Now, why that matters is because when you have holes next to each other, not only have a stress concentration coming from here, you have a stress concentration coming from here, so they can interact and cause even a higher stress concentration. So that's why this is useful to understand. And there are a lot of scenarios in vehicle designs where you're going to have biaxial state of stress with a row of holes, and you need to consider that. Again, fine elements can be used, but if you can do it by hand, why not? You're going to have multiple U notches. Scenarios like that could occur. You can have the scenario of a slot, lateral slot with circular ends in a member, a reinforced circular hole as an example. Here's the example of rectangular hole with rounded corners. Really nice. And you're going to see the R there, so you can look at that R. And you can see how this K depends on the R. You have an off-centered here, circular hole on a membrane cross-section. And then you have the V notch here in a member of rectangular cross-section. And then you have this bending applied. Other design plots you may see, this comes from Advanced Mechanics of Materials, edition 6E, figure 14.16. You're going to find other design plots just like that in multiple books. This for semicircular grooves, this for circular holes and fillets. Other types of plots you're going to see, these are other design plots you could see, and these are more complicated. So this depends on, for example, this T divided by rho, and rho is the radii curvature. T is this distance from here to here, and then you have B over rho as well, and B here means this distance, for example. It depends on which figure you're looking at. But you can see that these plots can get quite enhanced because on this side, you choose where you are, and then you go to this side to choose where you are, and the intersection gives you the answer. And it shows you how to use the plot. So it should be fairly simple um, to use. And these plots work fairly well for a lot of designs. A lot of designs. If you're wondering how to use it, if you're a number right here for T over rho. You come here, choose 5, and then draw a straight line. And this is ACC, right there. Um, it gives you a stress concentration factor, basically. If you have a relatively small notch within another notch, so I have this, I've seen this scenario before actually. If there's a nick or dent within a hole, you can calculate the stress concentration factor. And so it's going to be KT1 from the hole, the bigger hole, and then KT2 from the smaller hole, and then you multiply them together, and that'll give you a total stress concentration factor. That stress concentration factor can be large, but this will overestimate KT because a small notch is not embedded in a homogeneous stress field. So likely it's going to be overestimated, but if you have to do a hand calc to show good, it could be good enough. Modeling micro features. So say you have pits and issues within the design, uh, and that pit was within another pit. You could then use these formulas. So pits can be locations where fatigue starts to initiate. The cracking can initiate due to fatigue. Another point I want to make is stress concentration scaling. So if I have this diameter d divided by w, and that ratio is the same for both scenarios, but the width w here is larger here than here, the width. Yeah, the stress concentration is going to be the same KT, but it's going to have different stress gradients. And the larger specimens, this larger sample here, is going to have larger volume, larger notch surface area for highly stressed material. It's going to have a defect somewhere that's going to get it, can get this one in trouble faster than this one. So scaling effects could happen, while KT is the same for both. So KT in both of these cases, probably close to 3. Design guidelines for shafts. This is a poor design, for example. That's a sharp corner. I've seen a lot of people have those designs. You're going to round the fillet if you can. That'll be the preferred approach. Um, and that will help. That will stress relieve the sharp corner and help you out with the design. Sharp corners like this need to be rounded here. Um, yeah, so there's a sharp corner here. You can relieve it with grooves. Here I have a sharp corner. Relieve it by putting a fillet. Those are good design practices. Instead of bringing this stress concentration all the way to this shoulder, bring it just below where I don't have this stress concentration from this one interacting with this one, right? So these ones are too close to each other. That's going to increase it. So you want to be smart about where you end some of the features. These are very important points. I've seen a lot of failure initiations and shafts and things like that because things were not considered in that manner. And the idea is to really increase the distance between stress concentrations. Let me cover one more final topic before we end the lecture. And I want to cover something called the Neuber's method. The idea is there's a lot of problems you're going to encounter in industry where there's a stress riser, and that will cause the stress to be above the elastic limit. So we want to consider the effects of plasticity at the stress concentration and how the load redistributes. Finite elements will require a lot of elements. High stress gradient regions need to have like very small element size and a realistic representation of the nonlinear material stress strain behavior. So we need a good mesh refinement, and if you don't have one, a closed form solution is better. So I think the first step that you want to use is to determine KT for the geometry under consideration. And once you do that, you can also compute the nominal stress using the modulus to determine the nominal strain. So If you know the nominal stress, use the modulus to calculate the nominal strain, and then calculate the stress, the relationship here. Um, and this is what we want to be using to find the max stress. I'll show you how to do that, how to find this. But this is based on the energy method. So, uh, yeah, so as an example, this infinite width, far field stress, the right hand side of this equation will be 3 squared, because if I have a hole here, this will be 3 squared times sigma naught. And then this strain can be found. That's just sigma naught divided by E, the modulus, because stress equals E times strain. The modulus times the strain equals stress. So I get 9 sigma naught squared divided by modulus. Okay. So what we can do now is I know the stress strain curve. I know that. I know the stress strain curve for the material. I know that, right? And I know what sigma times epsilon is, which is a value. This is going to give me a number. So say sigma max equals epsilon max times equals some value. I can solve for sigma max equals that value divided by epsilon max. And what I can do now, I can plot that sigma max versus epsilon max, and this is that curve. Okay. And so if I had a linear material, I'll have a huge stress. At that strain, at the same strain level, I have a huge stress. It will be off the charts. But by using this correction, what I'm doing is I'm trying to calculate, hey, what is a realistic stress if I were to account for plasticity? And yeah, that's a method. You take the stress strain curve, you plot it, you know this right side of the equation, and then you plot this curve. Say this is like 5, then you plot stress equals 5 divided by epsilon and plot it, superimpose it here. That is going to be your new stress and your new strain corrected for plasticity. That's called Neuber's method, and it simplifies a lot of numerical solutions. So you don't have to even use finite elements. Now, it doesn't mean it's going to be perfect, but it's going to be close enough, within like 10-15%, which may not be perfect, may not be the best, but it is a good first step. And so now, what if I don't want to do hand calculation like this? I want to use finite elements. So maybe I just take the stress here. Say I had the stress. It was a linear elastic model, linear elastic with no plasticity. So I take that stress, and that stress, once you know that stress, you can calculate, and I'll call that stress nominal. I can calculate strain nominal. E divided by stress nominal divided by E, the modulus of the material. And once I have that, I can calculate the right side of that equation as sigma nominal squared divided by E. And you say, well, what happened to KT? Well, if it comes from the model directly, and you have a very nice fine mesh density, then stress already includes a stress concentration factor. So this is really 1 if you're using a finite model. So all you do is calculate this number, solve for stress, and that will give you a number in the top divided by strain. And now again, you can plot stress versus, stress here is a function of strain. Take the stress strain curve of the material, which is this, plot this which is sigma epsilon that I just calculated. And this came from the model, FEA. And where it intersects, that's your real stress, a more corrected stress and strain corrected for plasticity. Why? So, it's possible that stress FEA came out to be way out there, way out, way over here. It's going to give you huge stress. What Neuber's method does, it corrects for that using energy methods. But again, if you don't have the finite model and the finite model is not refined enough, you have to use closed form solutions. And that's where this formula can become handy. There's these two books here, log analysis and bear analysis, are great references to look at closed form solutions for various configurations. I encourage you to look at that. Okay, with that said, thank you so much for listening. Um, this great, I love stress concentrations. They're a lot of fun.